So today we'll continue with Professor Oleksandr Kyriienko's lectures. I'm reminding you that Dr. Oleksandr Kyriienko is a senior researcher in the University of Exeter, and right now he will continue the lecture on quantum machine learning, and specifically on scientific quantum machine learning. So Oleksandr, I'm giving you the word.
It's already the last day of the conference and summer school, so I hope everyone enjoyed it, learned a lot. And I should say this day will be difficult because we are moving towards the most complex part of the subject, but I hope everyone gets something out from this. Okay. So you could see the screen. Let's start. Today I'm going to discuss something that was just born in last few years. And before I proceed, I should actually explain what is scientific machine learning first, so that we know what is quantum scientific machine learning. Scientific machine learning is a nascent field of research in classical machine learning, where you use neural networks and other approaches to solve that data-driven problems in scientific computing. For instance, this could be fluid dynamics, mechanics, thermodynamics, theory of stochastic processes. So you say, in this case, I'm not so much interested in classifying images, cats, dogs, or fashion MNIST or ChatGPT, but I'm interested in solving physics-related problems, and that's what people in industry care for. So scientific machine learning will use neural networks as models for some processes, physical processes, or, for instance, chemical processes. One example that I know is that neural networks and specifically scientific machine learning was used for to help producing Moderna, one of the vaccines. So this has already some significant impact. And quantum scientific machine learning is the idea of making the quantum top up from classical SciML and use quantum neural networks and use some approaches inherent to quantum to solve open problems. So we return back to yesterday's lecture, and there I try to provide an overview of all possible tasks in machine learning. We have already considered regression. Now let's look into all other tasks, and maybe we cannot cover them in depth, but at least I'm aim to introduce the classification problems and also the solvers for differential equations that I've been working on. Another reminder that once we want to build quantum models, we need to use quantum neural networks or quantum kernels. So let's recall again, what is a quantum neural network? It's a set of operations applied to qubits. You have a fixed number of qubits. Then you apply a feature map, a unitary that encodes the classical variable x, so that's your input, or it may be a quantum state. Then you don't need a feature map, but your process of creating the state is actually producing features. Then you perform a measurement adaptation. So that will be either variational or fixed unitary W, and you could also re-upload. So you could repeat many times the same procedure. Finally, you will do the measurement. You can measure individual operators for each qubit, some expectation value of, let's say, Z Pauli operator, X Pauli operator, or you could combine them all together and measure probability of certain bit stream. Once you have found what will be the measurement result, you evaluate a function. And the function can be scalar, but you could also make a vector. So imagine this one will be a vector with all components. So in principle, this is all very flexible, and it depends on your output that you want to reproduce, your input, and also depends on the properties of your feature maps and the variational circuits. So once you have this quantum states, which I will call the QNN-based quantum state, you could evaluate a cost operator and get a latent space value of the function. And that will match to certain problems that you would like to solve. And just yesterday, we've been discussing what are the options of different feature maps. And I have explained that depending on how many times you perform rotation, how do you structure it, which kind of circuits do you apply, you can have feature maps that have different capacity, expressivity, and trainability. So this is just one slide. Maybe I should not get too much in details, but this is just one slide to show that it's a very active field of research, finding correct feature maps and toolboxes for working with these problems. So this work we just appeared today in the morning on arXiv. I didn't have time to add identifier, but you could figure it out. So in this work, we proposed a new type of feature map that maps your data into exponentially large space of Chebyshev polynomials. And moreover, each state labeling the Chebyshev state, Chebyshev basis, is orthonormal, which means you could easily go between computational space to the Chebyshev space. You can go to Fourier space with a Fourier transform, and that you could go in between the Fourier and Chebyshev space. So for instance, from computational basis to Chebyshev space, what we developed is a quantum Chebyshev transform. It's a different circuit from Fourier transform, but essentially it performs the same operation. It maps any state in the bit basis to individual Chebyshev state. So that's one example that you could still build some new approaches for efficient data embedding. Second, we briefly discuss the how do you compose a quantum ansatz, and here there are certain rules, but generally it's up to your creativity. How do you structure your ansatz? So the most popular ones corresponds to the hardware efficient ansatz. What is a hardware efficient ansatz? It's something that was natively suiting the superconducting circuits architecture, but now it's used widely, even if you are not tied to specific hardware. So let's look at its structure. First, you have rotations, and each rotation will have angle θ1, θ2. You would have θ3, θ4. So in principle, already within one layer, you have 2n independent rotations. Why do you need these rotations? Because you want to adjust locally the basis into arbitrary form, but only locally. So you do not correlate the circuits, but you could individual qubit states rotate on the entire sphere. So strictly speaking, it would actually help to have 3 gates, so Ry, Rx, Ry, because in that case, you really cover the entire Pauli, entire block sphere. And then after you have applied rotations, then you need to do the entangling operation. So to entangle operations, you would need to apply the pairwise either C0 or CZ operations. And in principle, we are not restricted to one gate set. So this is a hardware efficient part. If you have a hardware that can apply CZ, just go for that. If you want to use some unitary that just entangles qubits, it can be there and it will be fixed. If you don't apply entangling operations, the state will be trivial. If you just apply entangling operations but don't have sufficient tunability, your expressivity is limited. So you cannot access certain parts of the model. And the rule is, if you have n qubits, you will need to have the depths of the same order just to reach all possible states in terms of expressivity. It does lower the trainability, and that's the main problem, but okay, we have trade-offs pretty much everywhere when building these protocols. Here's another example. It's just RY rotations, and I remind you that if you apply RY rotation, because you generate cosine of theta identity minus I sine theta y. What happens is that the product of minus I and y operator, they give you a real matrix. So that's actually good if you don't want to create complex amplitudes. And that also helps, for instance, to obey time reversal symmetry. You also have what is known as QAOA ansatz, or sometimes Hamiltonian variational ansatz. If you take just some fixed unitary corresponding to all Hadamards, you have created superposition of all possible states. Next, what you need to do is apply the Hamiltonian evolution, but controlled by a single parameter. So gamma 1 is limited. And next, you apply rotations that do not commute with this Hamiltonian evolution, for instance, Rx. But again, beta 1 is the same everywhere. And that's a difference. It's very different from hardware efficient ansatz. Why? Because in hardware efficient, you locally rotate all qubits and then you entangle. So you very quickly reach configurations that become that are impossible with other unitaries, but you pay the price of trainability. In the QAA type ansatz, you only have, let's say here, you only have 4 parameters. The states are entangled, they are sufficiently complex, and they may suit specific problems, specific Hamiltonian, but they will not solve generic problem. So if you have a good understanding of what kind of ansatz will solve your specific problem, you could convert it into QAOA type ansatz, reduce the number of free parameters, and ultimately win. If you don't know initially what kind of expressivity you need, and if it doesn't have any symmetries, you should always start with a hardware efficient ansatz just to understand these questions. And in principle, I should say that there are many other type of ansatz. For instance, it could be related to tensor networks. And the idea is that you do not correlate all qubits, but you create entangled blocks. And then you will only correlate a part of these blocks and read out information here. So tensor networks, 3 type ansatz. Convolutional ansatz that I will describe a lot. So basically, you can think about preparing the state that's non-generic, that in the end leads to a non-trivial measurement only on 1 or 2 qubits, but it's sufficient for solving your problem. And that what happens, you don't include all correlations, but you only include correlations in this cone, which is required for representing a model on 1 or 2 qubits. So again, it's an open research. Nobody knows the perfect ansatz for one specific situation, but we are getting different recipes of how to build them. And we also briefly discussed yesterday the measurement operator. So sometimes I will just call it cost operator, and that could be anything from just a single Pauli operator, top or bottom, magnetization, so sum of all z operators in x and z direction. Sometimes it could be, let's say, correlation, I, j, or neighboring correlations. So there are different options, and you just take your state that you prepared with variational ansatz with your variable, measure c, and that will be your function. So that would be all for the toolboxes we have developed yesterday. Now that we know the tools, we could continue with the circuit differentiation. Why? Because we need to train these models. And second, because later we would be introducing differential constraint into quantum models. So the general rules of optimization are such that you start with some easy approximation to your optimal solution, or just some random state of your parameters. So you start with the state, and later you perform a gradient descent on the landscape. So here, for instance, in 2D, it's shown as this curve until you reach the global optimum. Of course, if you have increasing number of parameters, that becomes difficult, but it also depends on the landscape. So for a landscape that's convex, so you could see it as just a bowl where everything points down, then you could reach the global optimum efficiently. But if there are many minima, it's non-convex optimization. In principle, nobody can guarantee you good solution, but heuristic works, and for certain problem, you do get high quality results. That's effectively how classical machine learning became so efficient. So you start with some initial state, you perform a gradient descent in the stochastic way. Usually you would use Adam. That's if you know how to differentiate your functions. And you could also use numerical approaches, LBFGS, and many others. So types of optimizers for these problems have been studied extensively. So you could find in the literature suggestions, but generally I would still encourage everyone to experiment, try something, see what works well for your problem. And to estimate derivatives, you would need to use some tricks. For instance, the easiest way would be the numerical differentiation, and specifically finite differencing. Why? Because it doesn't require you to understand what is inside the function. You just consider it as a black box. You say there is a model f evaluated at point x. I could shift this model by parameter h. I could shift it also forward and backward, and I need to divide it by h, by this small step. Here the problem arises if you don't know your function, if you are not sure if it's highly oscillatoric or not, and generally quantum functions are highly oscillatoric. then choosing the steps become a problem. And if you don't know your function to high precision, and this is true in our case because we need to repeat many times the same procedure until we get small variance for the function. If you do find a difference, and you amplify the noise. So if you don't know the exact value of the function and you divide it by a very small number, you get very large error. So find a difference for our case is possible. It is applied in many cases, but it's not preferable just because you have larger errors. So automatic differentiation in this case is preferred. And here by automatic differentiation, I mean any strategy that can give you derivatives up to analytic precision, and you have a clear strategy what function evaluations you need to do to get the f prime. So in principle, automatic part comes from if you know the rules and you just apply them under the hood, you have access both to function and derivative, second derivative, without even specifying these rules. They're already built in your software. So that's what we want to achieve. And the way we are going to achieve it for quantum circuits is the parameter shift rule, which is derived for involutory operators. So I will explain a little bit what involution means. And I will say that any quantum circuits that we have can be written as the cost operators that we would like to measure in the end, after the application of parameterized unitary operators that go into a chain. And imagine that you would like to differentiate this model with respect to specific parameter. So here on the figure, we have mu parameter, and the rest will be labeled theta 1, theta 2, theta 3, theta 4. I have also chosen to represent it by theta, just for convenience, without a subscript, but yeah, that doesn't really matter. And once you have your function expectation value, you could say there are parameters that you do not differentiate, so the unitaries effectively remain constant, and it's convenient to just consider theta bar as anything that's not differentiating, so you consider it constant, and x is a parameter that you would like to differentiate. Then you split your model into the modified initial state. Then you have your effective operator in the middle, the cost operator that you measure in some modified basis. So keep in mind that all these unitaries are now considered constant. And the only unitary that you need to differentiate is u of x. So let's see how this model can be actually differentiated, and do it just now. Imagine f of theta of x such that there is this state psi theta that it does not depend on x. There is u of x dagger, c u of x, and we collected the rest again in psi theta. This will be generally true. I could also specify that the operator in the middle is also theta dependent, but what we want to differentiate is this function with respect to x. And for that, I will need to apply the product rule. So I will differentiate u dagger of x and I will sum it with the derivative of now of ux, leaving u dagger. So we have a combination of two terms, and that is very important. That's actually how parameter shift rule appears. So if I consider u of x, in general, it can be written as a complex exponent. So I remind you that how quantum mechanics works. We have the x, and we have some g operator. We call this operator generation of a unitary, generator of a unitary, which can have different properties, but no matter how G looks like, we will do the following. When we differentiate du of x by dx, we just lower minus I G in front. This is always true because you could check it by simple Taylor expansion. If you expand an exponent and differentiate with respect to x every term, you will be just getting minus ig to certain power. You collect it back and you see that it's because g commutes with itself, differentiating this unitary is not more difficult than just differentiating a scalar function. And if I use these rules, I would actually get psi theta. I will get I in front, and there will be minus ix g, or actually plus because we have dagger. There will be g c theta minus ixg. And the second term will have a minus, because what I have done, I have differentiated now ux, and I pulled out minus ig. And the order will be reversed because I now acted on the u, which was on the right side from C operator. So altogether, the derivative of our quantum function f theta of x becomes just a difference between g c theta and c theta g. So it is a commutator. And we have an I in front. We have the same model, a u dagger of x. We have the commutator, g c theta, u of x, psi theta. But there is an important implication here. If I look at the state with the commutator and at least one term, this state cannot be seen as an expectation value, because we don't have an operator in the middle, psi and psi complex conjugate anymore. We have a modified state. And since it's not expectation, it is an overlap, measuring it on a quantum computer will require different tricks. And overlaps are in principle are complex. So you will need to measure the real and imaginary part of the overlap of two quantum states. So that's possible, but that requires much more work. And ideally, we should develop something easier, some different technique. And the idea of parameter shift rule is converting this structure with a commutator to convert it into estimated expectation values. So how would we do that? Now comes the part of involution, which tells that if I have an operator g squared that's equal to identity, then I can write its exponent as a cosine of x1 minus I sine of x g. And what if I substitute x equal to pi over 4? In this case, I will get cosine pi over 4, which is 1 over square root of 2, and sine pi over 4, which is also 1 over square root of 2. So I have got minus ig square root of 2. And if I do plus minus pi over 4, that will be plus minus plus ig. So I created the superposition of something that's constant and something that generated my unitary in the first place. So the whole idea of parameter shift rule for this involutory operator is shift my unitary u of x with an additional u of x and u pi over 4. Because in this way, I have generated the term that corresponds to same u of x plus, or in this case, minus I u of x g divided by square root of 2. And at the same time, I have generated for u dagger of x, I generated a u dagger of x, u dagger of pi over 4. So I have reversed signs. And if I just take the state with pi over 4 shift and subtract it from the state with minus pi over 4 state, what happens is that I completely eliminate the constant part with 1 and g, and it's in the middle g. These terms cancel out, and what I only get is the terms corresponding to my c operator times g and minus g times c. So if I exploit the properties of my generator g, and if I combine two evaluations, I can reduce the problem of measuring the commutator into a problem of just evaluating the model at two different shifts and subtracting them together. So this strategy is known as a parameter shift rule. Sometimes it depends on the notation, could be a pi over 2 shift, pi over 4, but that's the overall strategy. You don't know, you don't evaluate the function numerically, you don't evaluate derivative numerically, but you have a full access to analytical derivative because you reproduce exactly the commutator. And there is one more approach that you could use, which we've been developing for cases where g squared is not equal to 1. And that actually happens for many operators. They are not involutory. So what we've been looking at is the decomposition of your g into separate projectors. So by spectral decomposition, you know that any diagonal operator d can be written as a sum of projectors times eigenvalues. And if I just rewrite my model as I did before, I can collect the terms that correspond to different overlaps. So these are not expectation values anymore. You have overlaps in here. And what you get is terms that are weighted by spectral gaps. Then I say, fine, I don't have access to overlap, but I can just call them some variables that are unknown, and later I would like to find them. What I do know is the spectral gaps for this model, and I'm interested in specific non-zero and non-degenerate differences of eigenvalues. If I have found all these eigenvalues, I will later substitute them into my sum. And the trick is to expand your function under the shift in this diagonal basis, where we will see that exponent of your initial spectral gap times x will also be shifted from that position weighted by the overlaps. So if you now take the difference between shifted to plus and minus side two states, you will discover that the difference is contained within this sign of your delta, the shift, times the spectral gap, and you will need to sum over all possible gaps. So if you manage to evaluate the functions at two different shifts, you have some information about the system, but not all, because you don't know the coefficients RS. But if there was just a single gap, the entire sum represents just a single term, and your derivative can be evaluated by taking the difference between two shifted functions and divided by sine delta times delta capital over 2. And that becomes a generalized parameter shift rule, because it means that in principle, if delta is very small, I can reproduce the finite difference. If delta is such that two functions are distinct, two function values, in this case pi over 2, it becomes just a regular parameter shift rule. But I could generalize it to any possible shift, and I could also do it for any generator. It will require more evaluations, but that's essentially up to you to decide how do you parameterize unitaries that you differentiate. And I should also mention that our understanding of circuit differentiation improves. So we are trying different approaches, and there are many groups that work towards this problem. Why? Because we need to differentiate when we optimize models, and we also need to differentiate when we actually are trying to embed differential equations in quantum computers. Okay, so I will stop for a little bit here to take questions. Maybe you have any questions about parameter shift rule, and just put them in the chat, and then we continue. Okay, just a short summary for everyone. Differentiation is important. It's the essence of machine learning. The ability of differentiating models helps you to find optimal weights, optimal parameters for these models. And if you look at the development of deep learning, so the scale of problems that we could consider, it was really enabled by fast differentiating techniques. So we should expect the same is true for quantum.
So, for example, when we're applying, I have a question. So we now have a method of differentiating function, like in the circuit. So can we, for example, apply it for gradient descent? Just
yes. So that's exactly one of the reasons why we want to have differentiation. So you get a function parameterized by a vector of theta's. You want to find the gradient of your function with respect to all theta's, and then depending on the this gradient, you will give instructions where should I move my state. So you will do updates, and that follows exactly the gradient descent. It could be it could include just gradients. It could include higher order derivatives. It can be evaluated with the rules can be stochastic, but in general, yes, the idea is to do gradient descent. And if you can have analytical differentiation, you don't lose the precision unless unlike numerical differentiation. So you could do it at much larger scale in general. For quantum computers, it still involves sampling. So even I should probably stress that if I have a function f of x on a classical computer, I mean, that's just a scalar function. But if I build a model on a quantum computer, I have instructions how f of x will look like in the limit of infinite number of measurements. But in principle, when I measure, I only have the finite number of shots, which means there will be a variance. So I don't actually know exactly the function. And this variance will be state dependent, because for some states, if it's just a zero state and my model is extremely simple, it's just like this, we know already the answer. It will be 1, and there is no variance. So if I do the z squared minus z0 squared, that's 0. So you have no variance, and that's actually helps, but in majority of cases, you don't know your state, so you cannot predict what state do you have. So you expect some variance, and if you are trying to differentiate the function by finite difference, and that's the problem, because you will be taking not genuine values of f of x, but your estimators. And even if you do parameter shift rule, you have a good idea of f prime of x, but that will be the average that you measure. So if you only have few shots, you also don't have access to perfect derivative. It comes through sampling, and that you need to account for. How does noisy environment affect differentiation? Yeah, that is indeed the question, because I mentioned the variance as the problem, but it's statistics. So assume that you have perfect device, you just repeat it enough times, you know that you collapse, so variance decreases with number of shots. So you say up to certain precision, I differentiated it well. But what if you have noisy environment? Your function will now look different. So the same functions that you have considered to be oscillatoric may, for instance, drop down. Why? Because you encoded x in the parameters that's related to time. And we know noisy environment over time will flatten the function. So if it was a magnetization and it drops to some low values as a function of time, instead of the perfect model, you will be differentiating something different. So instead of this trend, you got another trend. And noisy environment is actually first corrupting gradients, and thus it will impact a lot the gradient descent. So you could be trapped in some minima, or you could just go into erroneous solution, because what your model should be is actually different when you implement it on the noisy device. How can we combat it? The best shot is to do error mitigation. So error mitigation is a technique that says, okay, even though I have errors, I can repeat the same experiment in different bases, and I could average over all these results such that I don't have a biased solution. So maybe in some cases, in some encodings, I have a trend of going down. In other cases, I have a trend of going up. And if I average that, I will be closer to the actual function. So error mitigation, one idea. Ultimately, that will be error correction for quantum devices. Okay, good. Now let's continue. So we've been talking about regression. Now let's discuss classification. And classification in quantum machine learning follows the ideas of the classical machine learning, but there is an important difference. And the difference is that if I take a classical data, let's say an image, I have no problem loading my image into the classical neural network because, okay, the number of pixels is quite large. I don't know, up to 10,000 pixels per image. I also have a color information, but it's still a manageable vector. So I can load the data, and then I will process it by taking this input, weighting it into hidden units. I can perform what's known as a convolution. So I will gradually decrease the number of neurons that process information. And when I do convolution, I only keep the relevant information about the system and prune anything that's unnecessary. So I have started with the entire data that was pixelated image. I loaded it as a vector. I started to reshuffle these elements of the vector and distill only the information that I want. Ideally, it will be a set of features. So for instance, the shape of ears, the eyes that are slightly different, the whiskers. So that information will be essentially for understanding, is it a cat or a human? In this case, so is it the name given by machine or classified by humans? It's entirely up to humans to decide. So for the machine, how it happens, you need to, this is supervised learning in this case. So in supervised learning, what happens, you have images, and then you say, as a human, I understand that this image is different from another image. You probably know when you do CAPTCHA, and just to make sure you are not a robot, you need to distinguish how many bridges there are, or bicycles, or whatever, or traffic lights. That's exactly because you as a human can attribute a label to that image. And for machine, it's just cat is 1, dog is 0, alligator is 2. So you give these labels in the form of either binary for binary classification, or some multi-class label, and machine can build the connection between an image and this label. That's it. You cannot translate it. But if we are talking about natural language processing, that's where machines can say something. The labels that are just like binary can be translated in the text information, but that's a different subject. So on top of classification, you need to do much more fancy stuff. And we have this idea of classical machine learning, and the goal is to build a model that takes an input and predicts something. And this something is different from just a scalar function that's a wavy line as a function of x. But if you do the prediction, your function is more like a step. So anything that's before critical value will be a cat, over will be a dog, or vice versa. And this model performance depends not only on which kind of functions can you build, but can you generalize on the previously unseen data. And that's where machine learning is different from regression. So regression can, given the set of points, can give you some dependence, but it's not given that new points will actually have the minimized error, so the in classification. But for machine learning, the generalization is extremely important. Ability to predict information about new unseen data points. And what I'm going to discuss next is that quantum machine learning can provide advantage in the learning itself. So if you are deciding cat or dog, it's true you don't have a pure binary model. So at least in majority of cases, what happens that you get your probability of x scaling like this. So you have an output neuron, and it's even more applicable for quantum machine learning. Your output neuron, P of x, could be probability of observing 0 started from loaded data. And 1 minus P of x will be probability of 1. Fine, which means you will be bounded in between. But you could also have 0.9 value. So then you set up the threshold, and then you say at certain threshold, I call it a cat, below I call it a dog. That's it. So you want to make this boundary as sharp as possible, but in the end, yes, there will be some error when you classify images. And more specifically, if you want to try it again, the quantum circuit learning paper has the simplest example of classification with supervised approach. So you take your data, which is a two-dimensional, encodes two-dimensional vector. So you have x0 component and x1, and you have many points. Generally, imagine this is x1, x2. Each point is a position in a 2D plane. And you have, let's say, 50 points. So each dot is a different data point. Then you have labels. And labels for each point I will be in the class 0 or class 1. In this case, they decided not to do it just 0 or 1 for the same parameter, but they wanted to encode it in the vector of 1, 0, 0, 1. And this class will be associated later to 2-qubit expectation and not 1. You could choose it differently, but that's what they have decided. And then they test the cross entropy. A cross entropy is a measure how my supplied y, so my label 1001, is different from evaluated label f of x. And the f of x will be a result of the same QNN with measured 2 qubits. So what they get is the following QNN output, that if you evaluate the labels, they predominantly fall into class 0 in here, and otherwise it is class 1. So what you do, you draw a decision boundary, and decision boundary is not sharp in this case, but on average, it will explain that if you give me an unseen data somewhere here, with high probability, I will specify that's class 1. If you give me it somewhere at the boundary, okay, it depends on the setting the threshold. So most likely that the error will be coming from, but you do generalize well. And this idea of nonlinear decision boundaries are specific to deep learning and the corresponding quantum neural networks. You could also build linear boundaries with kernel methods, but that requires a slightly different approach. And if you build the probability of observing or class 0 or class 1 with a measurement of 2 qubits, you could also imagine that there are options of doing multi-class classification. Now, the only problem, in my opinion, in this case is the embedding, because you try to embed two variables, but what if you have 30? That becomes a problem, because building this decision boundary for 30 features would require you at least loading each feature information. But if it is an image, and if you would need to do it for 30,000 features, loading individually per qubit rotation each feature would require you either 30,000 qubits or 30,000 rotations applied in series. So if anything, this is the bottleneck of quantum machine learning approaches, because quantum computers are not very good at loading classical data, unless you do some tricks and use entire Hilbert space. But if you have limited number of features, but there are non-trivial correlations between these features, that's where you may get an advantage. And if we want to see what's the state-of-the-art approach here is, that corresponds to the convolutional neural networks, but now built with quantum computers. So the idea is to take a wide circuit, and then after you applied the initial convolutional layer, so you correlated the features, you apply the pooling layer. The pooling layer means that I partially collapse the state, and depending on the outcome, I will apply a conditional operation V. So instead of just a full state, I get part of the information, but as I train the network, I will make sure that only the useful part remains. Then I again correlate the remaining. So this is already latent space representation. So it's not anymore the input image, it's information about the features. Then I apply another convolutional layer to make model more complex, pooling layer, and at certain point I will get just a single qubit expectation value that by probability can do just cat and dog. The reason why it's only one qubit is because if I take expectation value of z, it's between 1 and -1. So I can do 1 minus z over 2, and that becomes the probability. So it is a function between 0 and 1. And if I manage to find this, the critical point, that will give me an answer. So if I just go step by step what do we need here? We need an input, which is a quantum data. So quantum data is just a quantum state. And this quantum state can be loaded by feature map, or it can come from actual quantum experiment. For instance, some evolution and of spins that you later give to the computational device, and you say, what are the properties of this spin? Then you have convolutional layer, which consists of same operations, and because U1 is the same on every pair, it's translational invariant, so it actually has some properties that translating the image will not change the information. You have pooling layers that conditionally rotates something, and it applies effective nonlinearity. And then the full convolution will just finish the classification. So one way these quantum convolutional neural networks were applied is to classify phases and spin patterns. And the reason why these quantum convolutional neural networks were pointed out as efficient, because what you do is classifying not only the classical data sets, but also the quantum data sets. For instance, if you give information about the properties of some materials, wave function of that material will actually define whether it is superconductor or just metal. And that will be your label, just state of the system that you supply to a neural network that will collapse part of the information and get the only the label. The reason why I'm pointing out is to highlight the advantage of quantum machine learning for classification here, because usually we consider scaling in terms of all number of gates. So we say if my number of gates is shorter, my time complexity of the protocol is much better, and thus I win. But that's not what is relevant for quantum machine learning. In principle, the shorter time of evaluating the model will not give you the full advantage if to give accurate predictions, you need to learn on 1 million of cats and dogs. So imagine that you have a huge data set, so lots of images, and then you give it to 2 different networks and ask how well can you learn? The answer will be, okay, some network will just work faster, maybe with lower accuracy, but it will train to certain precision. But what if I reduce it from 1 million images to just 10? The approach that may take less time and be more accurate in for large data set will completely fail for small data set. So there is so-called sample complexity, which is scaling of your accuracy with respect to number of data points that you train on. And that turns out to be important for quantum computers, because the statement is that if you have quantum data and you give it to classical computers, you would need to give a lot of data. Essentially, you will need to repeat measurement many times and give multiple configurations, because you don't know the basis in which you need to do the measurement. If you give it to a quantum machine learning protocol, few data points will be sufficient, because you actually can perform the unitary rotations to adjust the basis and know exactly the decision boundary. And we already discussed that if you do everything right, there can be advantage in training these models and expressivity of the models. but the very distinct property of QML is generalization, that it is better for quantum models on certain tasks. And thus you will have a learning process that's more robust. You could also utilize the sampling properties of quantum computers. So if you say, I want to develop a generative modeling program, you will need to generate new samples. And that's easier for quantum computers, again, in certain cases. And you also have a memory advantage, so that you actually, when you load the data into quantum registers, you have exponentially many amplitudes. So even though it's not always that you need to use them all, you need to be very careful with expressivity, you still get the memory advantage because your states will live in the small number of qubits, but will contain a lot of information. Okay, and with these QML advantages, let me just mention that I don't know if it was considered in the previous lectures, but we also need to briefly mention vanishing gradients and barren plateaus. So anyone, can you write in the chat, was it already discussed, the barren plateaus or not?
Sorry, can you repeat what was discussed?
Barren plateaus.
I actually don't remember barren plateaus. No, I think it wasn't.
Okay, so then it is important. So everything I was describing you until now is based on having a model, having variational parameters, being able to optimize this model to match the prediction in regression or classification. I also mentioned that the number of parameters that you need to tune grows with the depth of your circuit, and so grows the number of possible directions that your state can take. So imagine it as a vector, but now in the on the hypersphere, so in like living in the very large dimension. And then you're trying to rotate this vector to represent specific states that solves your model. Finding the ideal state, the global optimum, is difficult, and that's a problem of trainability. So the statement is such that if you have a circuit depth that's small, specifically that's logarithmic in the number of qubits, then you have a circuit that is trainable, because you still have a small number of parameters to deal with. Then if you start to go into the ansatz with number of the parameters that grows polynomially with number of qubits, so the depth increases until this point, you will hit the vanishing gradient problem. And it also appears in the deep neural networks, but for quantum neural networks, the onset of this process happens much, much earlier. Why? Because the variance of each gradient drops exponentially with the number of layers. So here you could see, if you fix the number of layers in here, and you go from small number of qubits to large number of qubits, you will see for small number of qubits, you could still exhaust all possibilities, but for large number of qubits, your variance of gradients drops exponentially. And if this happens, it means that even though technically there is a solution, you will be stuck in this landscape, which is flat. And that's why it's called barren plateaus, because you cannot apply gradient descent. Each new move will not lead you closer to solution. You don't know where is the gradient lies. And at a certain point, you will hit this patch, but it may require exponential time. So it's an open problem in the variational quantum circuits. How do you find this situation where there are no barren plateaus? And it requires finding you a correct answer. So what was already developed are techniques when you reduce entanglement in your system to help avoid the barren plateaus, and where you construct your ansatz in a very specific way. So one statement is that convolutional architectures, because you only have limited number of parameters, it doesn't go into full depth, but it actually reduces the number of parameters like this, will avoid barren plateaus, because the gradients of such ansatz decrease only polynomially and not exponentially. So if you, another issue, if you consider uncorrelated and correlated parameters in these models, you see that the correlation between parameters keeps the gradients high, which means that you keep some information about the state, and you efficiently can you can efficiently navigate the landscape. So how does the size of the quantum system and the number of parameters affect the occurrence of barren plateaus? Yes, it is very important question. The number of parameters, it's pretty much the same plot that is shown here. The rule is, if you have the number of parameters, independent number of parameters that reaches the system size n, or larger than that, let's say n squared. So I have 10 qubits. If I already went into the depth of 100 layers, most likely I'm in the barren plateaus regime. So I can try to optimize, but I will be finding very weird solutions that never actually solve my problem. Because the number of possible states, I can prepare scales exponentially, but I am only given the polynomial number of independent parameters. So I will never reach the perfect model. And what I can actually do, I could reduce the number of independent parameters and make sure that each new layer does not represent entirely different unitary. So imagine that I do xy, 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 same unitary. Out of xy, I can construct z, but I will never go outside of xy and z subspace, an identity. So I, by interleaving the operations, I extended my possible effective rotations, but I never do entangling operation. In this case, there will be no barren plateau, because as long as you exhausted all choices and you have sufficient number of parameters, you could always find the correct rotation. The problem is when you, so in principle, you can, with a smaller number of independent parameters, repeated many times, you can find a perfect solution. But the problem is, now you restricted the number of parameters and directions. Maybe your solution, the ideal solution, is not, lies somewhere outside. So you actually needed entanglement to represent it. And that's a problem, because you make it trainable, so you actually can access all possibilities within the limited space, but you do not express the solution, and that's a problem. That's actually where you start getting the results that trainable, but have a limited accuracy. And if anything, from the quantum machine learning studies, we know that trainability and expressivity are competing with each other. And if you are staying at the level that I can still train it sufficiently well, so it does converge, maybe not perfectly, but it does converge, and you get the expressivity enough to solve your problem, that's a winning situation. So yes, it's a tough problem to solve, and that takes a very strong effort from the community, but that's what we need to tackle if we want quantum machine learning to succeed. Okay, so let me just briefly mention that quantum machine learning advantage comes from generalization in many ways. And the reason is that even if I train my laws to reproduce certain curve, it doesn't mean that given the new samples, I can have a high accuracy of prediction. And these prediction laws should be tested independently. I guess that's what was already covered in the beginning of the week. So you first have your training set and validation set. You train the model and you check, you do cross-validation. Did I actually manage to generalize? So this prediction laws for quantum states and the associated error seems to be exponentially better than for classical cases. Specifically, you say that if I have an ansatz with T parameterized quantum gates, my generalization error will scale as a square root of number of these gates. But for classical cases, this generalization error will be much larger. And the conclusion is that in principle, for very few training data points, you could already have quite high generalization capabilities. And that's one of the learning advantage of quantum machine learning. So where does it work? For instance, if you are taking the spin system for some Hamiltonian, you get solutions. So you get ground states from these Hamiltonians. And then in principle, it was shown that with few samples, so 30 samples, but sometimes even with just less than 10 samples, quantum machine learning program was able to generalize, so to get correctly all the boundaries between these spin models based on the very few examples. And at the same time, classical machine learning required many more samples. So if you do convolutional neural network as compared to quantum convolution. And that was actually done by Google. So there was a question yesterday, are there any larger scale experiments? I believe that's one of the largest, where they took 40 qubits. They tried to distinguish the properties of quantum states that involve 1,300 quantum gates. And they asked, the question they asked was quite simple. Do I have a state coming from unitary with time reversal or without time reversal? And they managed to separate the, draw the boundary between the two cases. With quantum machine learning, prediction was given the clear separation between the two. But conventional machine learning needed many more samples to do the same separation. And that's understandable, because if you collapse information to bits and only then you do some prediction, you actually need access to the basis, optimal basis to do the prediction. But quantum neural networks can adjust this basis and give you a high separation. Okay. So that was the part about geometric quantum machine learning, and that was the advantages of learning in general. And now I will briefly mention the recent advances. So really, like last year was full of geometric QML, which is a simple idea but difficult to implement in practice. And it tells us that if we want to build the high-performing models, we need to include symmetries in our models. For instance, if I know that my data set has a property of, let's say, reflection with respect to diagonal, so the labels, if I reflect, will be the same, that means I can encode this symmetry into the structure of quantum neural network. I just say, I only include the operators that upon reflecting with respect to diagonal will not change the labels. And then you say, fine, I restricted the number of possible unitaries. So you could see that here we have the same theta's. So I do not include like all possible combinations of X, Y, and Z with different theta's, and it helps trainability. So I can actually learn the model, yet my expressivity is good enough because I do have this symmetry of reflection. So I don't lose anything. And of course, classically, it will also be easier to work with these data sets. So not only you help the quantum machine learning, but it should be easier to do classical machine learning. But that's one way of building trainable and expressive models. So use geometric quantum machine learning. And if we have some information about the system, some physical information, we could include in QNNs and facilitate the learning process. Okay, so I don't have much time left, but if you ask questions now, and I will just briefly describe one example from solving differential equations and leave it there. Okay, no question it seems, so let me continue. And here I would just say a couple of words about PDE solvers that we've been developing with the idea of using quantum machine learning now to give solutions of differential equations and also learning from data. So the motivation is solving problems in scientific computing. You get a system of differential equations, and then how you usually proceed in this area, you discretize it, you put it on a grid, on some mesh, you convert your operators into matrices, you get your initial state, and in principle, you could imagine that quantum computers would be able to load these states as some vector psi, so state psi. Your goal is to find an application of inverse of A to B. So you solve the equation A times X equals B, and X is solution of your system of differential equations. So that's how classical approach work and how you imagine that quantum will also proceed. And quantum linear equation solvers were proposed already some time ago by Haram, Hasidim, and Lloyd, saying that yes, we can in principle do matrix inversion on quantum computers exponentially better than classical computers. But there was a problem because this is extremely deep circuit. So you will need many gates, many blocks. So each block is actually quite involved. You need to load this state that sometimes is problematic. And you also need to read out the state, which unless you have access to all amplitudes is extremely difficult. So that's was the bottleneck of quantum linear solvers, and same for differential equations. And what we propose is rethink it in terms of quantum machine learning and neural network perspective. So if we return back to the regression models, we've been just taking our f of x of theta and trying to match some curves. But we could also consider the derivative of this vector with respect to x. We could also get second order derivative. So in principle, if we have information about my model, but also derivative, and I know it via parameter shift rule, via automatic differentiation, I could just continue and compare how my derivatives and weighted models correspond to each other. And that's what we have done. We just took the model with feature map and the measurement, and then we applied the scaled feature map, and we were building a loss function depending on not just the f of x, but also derivatives. And that's what we call derivative quantum circuits. So taking the derivative with respect to x, if it's uploaded many times, will require you evaluating a parameter shift rule now 2n times. But we could also use this generalized circuit differentiation technique in certain cases where it's useful. And the entire approach becomes similar to physics-informed neural networks that are known in classical machine learning, which says that if I have a neural network and I would like to represent it as a solution of partial differential equation, I could differentiate it with respect to my input and also with respect to variational parameters, form a corresponding loss function, and if I optimize it perfectly or up to certain precision, I have solved the problem of differential equations. So in classical machine learning, this what's known as pins became extremely popular, and for certain problems with larger number of variables and equations, they were shown to beat existing solutions. So our hope is that we, for quantum problems, we can also get advantage of building a quantum model and, let's say, finding the solution and using this solution in some way. So we take the derivatives, we take the function, we know that the sum of those should give us 0, so that's the condition of differential equation, and you also have the boundary condition, which you need to match. You say that the distance between two should be minimized, that's a loss function evaluated on certain grid. If I found the minimum of this loss function, I got the solution. And in general, there are lots of questions to figure out, like which feature map to use, how do you handle the boundary and everything. But in these papers, we discuss all the good approaches. So now that I have described briefly the approach, let's consider it on some test problems. And the test problem we have chosen was some simple differential equations that leads to quadratic solution. So we have the true solution in blue, and we start with some model that represented by a quantum circuit. We train it, and after certain rounds of training, we actually match the solution. So generally, that's how the workflow goes. You set up a model, you set up a loss function, and then you minimize it. And the full workflow will be slightly more complicated. So depending on the feature map and loss and boundary, but you just collect a bunch of circuit measurements, and then you check how close are you in terms of equating derivatives and function itself, and did you solve the problem or not. We can try it for simple model functions. So let's say we try to come up with some complex differential equations with oscillating function and see how can we fit it with different feature maps. And we have also tried it for the quasi-1D Navier-Stokes equation, where you have three variables: temperature, velocity, and density. And then you test, can I find a solution for these variables as I go through the nozzle? So some flow through the small area of your nozzle. And how can we solve this? We do the same procedure, but we train our network to reproduce solution before the nozzle, and we use this as a regularization for the next stages of our training. And after we included two domains and we excluded the domain where the solution diverges, we have found the true solution of quasi-1D system of differential equations. So that was one example. How can you utilize the approach? And often you ask, okay, I have managed to solve some problems, but where do I see the advantage coming from? And what we found out that beating classical grid-based methods is actually difficult. But if you have a data-driven problem, so you don't have a boundary solution, but some data, you would need to train the system anyway. So then we have developed the model discovery method, where you take your quantum model, you have some input data that represents a boundary condition, and you have a system of differential equations that you don't know perfectly. You know it would be a Lotka-Volterra model, but you don't know exactly what are the parameters. You build a loss function that will include both the input data and the differential equations, and then you find the solution fits the best certain model. So for instance, in this case, you know that there are no x squared or y squared terms, but there are only the linear term and cross terms. And with quantum model discovery, we managed to represent it. And another example where I believe the important advances of these approaches corresponds to the generative modeling. So I have no time to discuss it in full. It's a very deep and complex subject. But what I should say is that if I have found f of x of theta as a quantum function that is scalar, I'm just doing something that's intuitively should be easier for the classical computer. But what if I actually represent p of x of theta, which is a probability distribution, which means that there is outcome x and there is some probability distribution. Our goal is to build p of x of theta as a probability of measuring certain outcome from the quantum state like this. And if I manage to create psi of theta that gives correct probabilities, then I can read out sample by just making a measurement from this psi theta. And we have found many different ways how this can be done, including the differential constraints and building model in the Latin space. So that's pretty much the active area of research in my group for the last 2 years. So with this, I believe I will just go to the conclusions that are far away. Yeah, here's that. So my conclusions are that quantum machine learning is indeed the powerful tool, but you just need to know the cases where you shall use it. It will not fit every problem if the data is trivial and uncorrelated, or you have huge amount of data. Don't try, or you can try, but don't expect quantum machine learning to help immediately. Second, the type of advantage you get is not always speed. I have seen cases where somebody complained, oh, with a single GPU, I could do much more than with the quantum computer. Yes, that will be true for some cases. So if you are looking for generalization, if you are looking for learning advantage, if you are trying to process inherently quantum data, that's where advantage may come. Or if you need to, let's say, solve differential equations in some multidimensional space and later get samples from that solutions of differential equations. In this case, you will utilize again the native properties of quantum computers. So overall, quantum machine learning is applicable in certain areas of data science, and we will be, like in coming years, we will be finding more and more examples where QML helps, and actually cutting down on those examples that are not suitable. With this, I will thank you for attention, and if there are any questions, please ask, but I guess we are getting into a break now.
Yeah, like I think we can take some time to ask a question. So like okay, I will ask this question by myself, more about like the differentiation methods which you showed here, like quantum differentiation on circuits. So does it mean that we can, for example, there is a method of solving like many particle Schrödinger equation on a quantum computer by like trivialization, for example. But if we like developed the differentiation method on circuits, it means that we can implement some sort of like quantum Rudicuta or like another like quantum analogies of a classical method of solving differential equations or something like this.
So in principle, if it's is it possible to rewrite this problem in terms of machine learning? Yes, it is possible. I believe so. The second question, is it the most efficient way? No, probably not, because we know the solution to Schrödinger equation already. It's e to the power of minus I ht. Like the exponentiation appears from the structure of Schrödinger equation. Because it is linear, you know that it's the exponential solution as a function of time. So most likely, if you work on expanding exponents, like you mentioned, the trotterization, it's a much better strategy than actually truncating it, telling to do Runge-Kutta and then doing it as a matrix inversion.
But, more natural way.
Yeah, I haven't seen it studied. If you ask a different question, Anton, let's solve this Gross-Pitayevsky equation, which is a nonlinear Schrödinger equation. Then you cannot apply just matrix exponentiation directly, and then you are back to the same problem. You have some nonlinear differential equation. How do I solve it? And in that case, like quantum simulation, unless you have exactly the same system, will not help. Then you start to form a matrix based on the potential, kinetic energy term, and interaction, and then you will be solving for that matrix. Then yes, then you may get advantage.
Yeah, it's actually it's good that you mentioned Rosputieski equation, because I was thinking that when you're solving it, one of the methods of numerically solving it is like fast Fourier transform. So if, for example, we can somehow, I don't know, embed this data. So can we try to solve this equation, for example, quantum computer using the quantum Fourier transform? And can it, for example, improve our, like, I know, speed or something else? In terms of, just like just a wondering question.
No, that's exactly what happens in many ways. You are choosing the suitable basis. Like, my research is a lot about finding the correct transformation where problem looks easier, and this transformation is mapping the bit strings to some, I don't know, let's say Fourier space. Then you could implement differentiation in Fourier space much easier than in the real space. Let's say you find operators that look easier, and then you will, when you read out the solution, you transform it back by the dagger transformation. Then you need to figure out how to introduce nonlinearity in that space, but okay, that's doable.
Mm-hmm. Yes.
Yeah. So it's playing with basis transformations. It's playing with a suitable, like the most optimal form that you don't lose much information, but you get the essence of your problem in that basis.
Okay. Thank you very much for answering. I'll also give a possibility for participants to unmute themselves, so if they have some questions, they can ask directly.
Yeah. Please do. I mean, I guess the main question from me: did you enjoy the quantum machine learning summer school in principle? Was it useful?
It's so it's a question for every participant. Yeah. It's also a question for me. Yeah, how did you think about it? I mean, we still have another like last lecture, so it's not the end. But anyway.
At least there is one positive feedback, so that's great.
Yes, understand. Just like many people already have time. Oh, okay. I think I was. Okay. Thank you, Oleksandr, for the lecture. I'm stopping the recording for a while.
Yeah.
1 second.